Hello, chemists. This is Ms. Placino, and you're watching lesson 6.1 on significant figures. In today's lesson, we're going to talk about what significant figures are and how they're used in calculations. Some goals for today's lesson. You should be able to explain uncertainty in a measurement and how it pertains to significant figures. You should also be able to measure using the proper technique to the correct number of significant figures. Perform calculations by applying the significant figures rules. Significant figures are usually something that is really challenging for first-time chemistry students, and it's going to have a very important role in the lab. So we're just going to try to lay the foundation for it today, and we'll be applying it more when we're taking measurements in the laboratory. Let's get started. Okay, I'm guessing you've heard the terms precision and accuracy before, probably in a previous science class. So given what you already know about precision and accuracy, I'd like you to describe the location of the darts, those little X's on the dartboard, the bullseye, in terms of precision and accuracy. So go ahead, pause the video, try that out, and then once you've got it finished, we'll start back up. Okay, so I'm guessing that the terms, or the definitions rather, that you have for precision and accuracy are as follows. Precision is the ability to get the same results again and again and again, and accuracy is how close you are to the accepted value or like the goal measurement. So if we take a look at this first bullseye, we are precise, but not accurate. All of the darts are clustered really close together, but they are not close to the bullseye. If we kind of look at the overall position of the darts for the second dartboard, we are not precise, but we're fairly accurate. Like if we took the average location, I bet it'd be pretty close to right on that bullseye. Dartboard 3, we are neither precise nor accurate, kind of the worst of both worlds. And of course, this final one is precise. They're all clustered together and accurate. They're clustered around the bullseye. These are the definitions that we use when we're talking about experimentation, precision, and accuracy. We use slightly different definitions for these two terms when we're talking about the precision and accuracy of instruments. And it turns out that significant figures is really related to how precise an instrument is. So let's get into it a little bit more. When we talk about instrument accuracy, you're just looking at the ability of an instrument to measure correctly. This is a function of calibration. If you take a paper clip and you stick it on your little scale in the lab and it tells you it weighs 53 grams, something is wrong with that scale. It's not calibrated correctly. So you'd have to go through and calibrate the instrument. If you're looking at something that is like a graduated cylinder, for example, we're going to assume that it is reasonably accurate. If it tells you 10 milliliters on a graduated cylinder, within a small range of error, it's probably pretty close to 10 mils. We can't really calibrate a piece of glassware like that. So kind of the same as accuracy in our previous definition. The difference really comes in with precision. We're talking about instrument precision. It's not you pick up that same paper clip and you keep putting it on the scale again and again and again and you get the same reading repeatedly. Instrument precision is looking at the smallest increment that can be measured by the instrument. Now, you might have a digital scale at home, like a bathroom scale. You stand on it, it probably measures to the nearest pound. If you look at the scales that we have in the lab, they measure to the nearest hundredth of a gram. If you were to go into a really high-tech lab, they might have an instrument, a scale that measures to the nearest 10,000th of a gram. Those are differing degrees of precision. So that's really all we're talking about with precision, is you've got your sample. You're taking the same sample and putting it on different scales in this case, and you are getting slightly different readings, not because something is more accurate than the other instrument or less accurate, but because they have different degrees of precision. The scale all the way over to the right measures to 3 places after the decimal point. It is the most precise of the group because it can measure to the nearest tens, hundredths, thousandths of a gram. Over on the left, this is our least precise instrument. It has to measure to the nearest whole number, the nearest 1 gram. So that's what instrument precision is. And when we are performing calculations and measurements using significant figures, we want to make sure our measurement expresses the precision of the instrument we're using. Just a little bit more on that. Again, we've got our 4 scales with 4 different degrees of precision. What the scale is telling you, in the case of this first one all the way over on the left, is that it knows the mass is somewhere between 110 and 120 grams. The ones place was estimated, so we would call it uncertain. If we go over one scale to the right, this instrument knows the mass is between 112 and 113 grams. The scale guessed. Of course, the scale is not making actual guesses, it doesn't think, but the instrument is having to estimate the tens place. So we would say the tens place is uncertain. You can make that same inference with the last 2 scales. Each time we are taking a guess or estimating at a smaller and smaller place. You might notice that it's always the last place in a measurement where the uncertain digit is present. So everything up to that last digit, the one that's farthest to the right, will be known with certainty that the final digit is always estimated. So we say that it is uncertain. So again, the number of significant figures in a measurement is going to communicate the precision of the instrument used. Really, what's the smallest increment that instrument is capable of measuring? It is not the same on all instruments. And the more places that come after the decimal point, the more precise the instrument is. Generally, also, the more expensive the instrument is. This is an extremely sensitive scale. I don't know how well you can see it, but let's see, tens, hundreds, thousands, 10,000s, 100,000ths of a gram. Extremely precise. So we'd want to communicate those places after the decimal point. All right. One time in the lab that's going to be really important to deal with sig figs correctly is measurements. It's easy enough to do on our digital instruments. It just kind of spits out the number and you record all the digits. For analog instruments, ones where you have to do the measuring, it's a little bit more involved. So let's say we're trying to measure the height of this paperclip. So the proper measuring technique that we're going to use is to determine first which each tick mark represents. So if I look at this first ruler, I've got 1 centimeter, 2 centimeter, okay. Every tick mark, every line represents 1 centimeter. I'm going to estimate 1 place further to the right. So 1 place further from the ones, that's going to be the 10th place. So my measurement using ruler number 1 should go to the 10th place. So I see about 2.8-ish centimeters, give or take. We might disagree with what that last place is because it has been estimated. Maybe you see 2.7 or 2.9 centimeters. That's okay. As long as we can agree that it's somewhere between 2 and 3 centimeters, we're good. Finally, make sure that you include the appropriate units. In this case, it is centimeters. There's 2 parts to every measurement, the numerical value and the unit. They both need to be there for your measurement to be correct. You try it out for ruler number 2. Hopefully you're coming up with about 2.71. And again, you might disagree on the last digit. That's okay. It was estimated. But now each tick mark represents a 1/10 of a centimeter. So I can say that this paperclip has a height somewhere between 2.7 and 2.8 centimeters. I'm going to guess at the hundreds place. It is my uncertain digit. Go ahead, pause the video, try these out. Measure to the correct number of significant figures and see if you can take a stab at what the unit might be as well. So pause, try them out, and start the video back up when you're done. Let's see how you did. So that first instrument, that is a beaker, and beakers we're going to measure in milliliters. I see about 28 milliliters. I know it's between 20 and 30. The tick marks represent 10 mils, so I need to estimate to the ones place. The second instrument, that looks like a cutaway of a thermometer, and each tick mark here represents a 1/10 of a degree. I saw this as 0.29 degrees, and since we're in chemistry class, we don't use Fahrenheit, I assume degrees Celsius. Again, you might see a different last digit, that's okay, but the measurement has to go to the hundreds place. This is an instrument you probably haven't used before, a burette. You might be wondering, why is this graduated cylinder upside down? Well, the answer is because it's not a graduated cylinder. I know I'm somewhere between 10 and 11 milliliters, more specifically between 10.5 and 10.6 milliliters. I got to estimate, I got to estimate the hundredths place. So I got 10.58 milliliters. Up next, we have a ruler. I'm going to assume that's measuring in centimeters. It looks like I've got 6 right on the nose. I can't leave it as just 6 centimeters. I've got to go to the correct number of places to express precision. Each tick mark represents a tenth. I need to estimate to the hundredth. Okay, I see just under 5.99 centimeters. If you saw it as 6, you need to include 6.00. I know mathematically 6 and 6.00 are the same value, but from a significant figures perspective, those are 2 different degrees of precision. Last but not least, we have a graduated cylinder. Each tick mark represents 1 milliliter. I saw this as 43.0 milliliters. Again, we might differ a little bit in the measurement, but hopefully that difference only comes in the final digit, the one that is uncertain or the one that has been estimated. All right, so now you've made your measurement in the lab and you're getting ready to perform calculations. One of the things you need to take into consideration is how many significant figures are present. So I just want to go over the rules that we use for counting sig figs. First one is an easy one. Anytime you have a non-zero number, a non-zero digit in your measurement, it is always significant, no exceptions. The difficulty comes in when you start looking at zeros. Captive zeros, so zeros that are sandwiched between 2 non-zero numbers, are always significant. It doesn't matter how many zeros are present. It doesn't matter if there's a decimal point or not. Zeros in between non-zero digits or between significant figures in general will be significant. So that would give us 3 sig figs in total. 4 sig figs, I'm not going to bother counting with that, but all of those digits are significant. Oops, sorry. Our leading zeros, zeros that are to the left of non-zero numbers, are never significant. This really comes into play when you are looking at measurements where you have less than 1. So these lead zeros, 2 of them in this case, 1, 2, 3, 4, 5 of them in this case are not significant. So this 0.0521, that has 3 significant figures. This measurement only has 1 significant figure. All of those lead zeros are not significant. Trailing zeros, so zeros that are to the right of non-zero numbers, are only significant if a decimal point is present. In this case, we have 1.900. I've got trailing zeros. Okay, they're only significant if a decimal point is present. Oh, I've got one. So all 4 of those are significant. Finally, we've got some numbers that we call exact numbers, and they have an infinite number of sig figs. So definitions, things like there are 24 hours in 1 day, or there are 100 centimeters in a meter. Those are definitions, and we don't deal with sig figs with those. We consider them to be correct to an infinite number of sig figs. Counting numbers also don't have sig figs. So like coefficients in a balanced chemical equation, that's not going to limit us to 1 significant figure. It's really just measurements that we make. All right, pause the video, try these out. We will review when you're ready. Let's go over these. The first one, 25 centimeters. This should be an easy one since there are no zeros. 2 significant figures are present in that measurement. Now zeros come into play. That lead zero is not. The captive zero is. 4 sig figs. Number 3, lead zeros are not significant. 3 significant figures. Number 4, this decimal point is going to cause all of the zeros to be significant. So this is a trailing zero with a decimal point. That's significant. Now I've got zeros sandwiched in between 2 significant digits, so they're also significant. 4 sig figs. Question 5, all lead zeros. Lead zeros are never significant. Only 1 sig fig in that measurement. Number 6, if you're working with scientific notation, we only pay attention to the coefficients, the times 10 to the whatever term. We don't look at sig figs. So we have 2 sig figs in that measurement. Again, we've got captive zeros in number 7. All of those digits are significant, all 5 of them. Number 8, 0 that's a lead is insignificant. I've got trailing zeros, but I've got a decimal point, so that makes both of those significant. Also 5 sig figs. Lots of zeros here. Lead zeros never are. Captive 0 always is. Trail 0 only significant if there's a decimal point. There is. 4 sig figs. And then question number 10 is the one that drives students crazy. Technically, the way it is written, there is just one significant figure. This doesn't come up a ton in the lab. You don't usually end up with a number like right on the nose, like 500. Some people try to stick a point there, suddenly making all of them significant. That's kind of a, I don't want to say it's cheating, but it's kind of a cheap shortcut to use. The correct thing to do is to use scientific notation. If I wanted to express 500 to 3 sig figs, I could go 5.00 times 10 to the third, 2 sig figs, 5.0 times 10 to the third, 1 sig fig, 5 times 10 to the third would be correct. Don't stress too much about that rule, and it doesn't come up too frequently. All right, so now you've taken the correct measurements, you know how many sig figs are in your measurements, and usually we've got to do some sort of mathematical calculation with them. There are rules that are going to govern how to do this. So we need to perform our calculations to the number of significant figures that reflects instrument precision, specifically the least precise instrument that we used. So let's say you were trying to find the density of something. You've got your mass at, we'll say 29 grams. You've got a volume of, looks like about 36.5 or so milliliters. If you just start plugging this stuff into your calculator, you're going to get a ton of places after the decimal point. Your calculator assumes that everything that comes after the 29 is a 0. In this case, everything that comes after the 0.2 is a 0. We don't actually know that. Our instrumentation isn't precise enough to know what's coming after, in the case of the mass, the ones place, in the case of the volume, the tenths place. So I cannot just go to any number of significant figures that I please. This is not communicating the precision of the instruments I'm working with. So there are really two main classes of calculations that we're going to deal with. We're going to use addition and subtraction. That's one set of rules. And then multiplication and division. And that's the one that tends to come up more frequently. Okay, so let's talk about the rules. Calculations and sig figs. So let's say you're doing an addition or a subtraction. So maybe you're trying to find the volume of an irregularly shaped object using water displacement. The final answer, so with the end of the calculation, has to have the same number of places after the decimal point. That's really the key here, as the measurement with the fewest places after the decimal point. So with addition and subtraction, we're not really counting sig figs. We're looking at how many places are after the decimal point. Let's say you've got something like 25.00 milliliters, and then you've got minus 18.3 milliliters. I'm not too worried about the math. I know you can do this subtraction. How many places after the decimal point can we have? Well, I gotta use the fewest, and I've got 2 places after the decimal point and 25.00. I have just 1 place after the decimal point and 18.3. So my final answer can only have 1 place after the decimal point, because we've got to reflect how many significant figures, or how the precision of our instrument using significant figures. So you would have to do some rounding here. I mean, you can just leave it at 6.7. Multiplication and division is a slightly different rule. When we multiply or divide, we have to pay attention to significant figures. So the final answer has the same number of significant figures as the measurement with the fewest. So just kind of in the same vein as addition and subtraction, our least precise instrument is going to dictate significant figures. So let's say you did something like, I guess we can use the example that we had from before. We had 29 grams divided by 36.2 milliliters when we're trying to find the density. how many significant figures can I express the density to? Well, I need to go to the same number of sig figs as the measurement with the fewest. I see 2 sig figs in 29. I see 3 sig figs in 36.2. So I'm really limited to just 2 sig figs. Something like that. These will become more and more ingrained the more frequently you use them, but it's really important in the lab in particular that you are correctly measuring to the correct number of significant figures to express instrument precision. And then when you go and do your calculations, you need to be consistent and express answers to the correct number of sig figs. So sig figs, again, they're are particularly important when you're performing calculations with measured values. So measured values, again, you're in the lab, you've measured a volume, you've measured a mass, you've measured a temperature. These are numbers that you've collected through using different instruments, graduated cylinders, thermometers, scales, or triple beam balances to get measured values. If you are going to just look up a value, like for example, you need to use molar mass or something in a calculation. If you've looked it up or you got that number just by punching things into the calculator, you didn't actually measurement, they're not going to impact significant figures. I know right now these rules probably seem kind of arbitrary, maybe a little abstract, but once we are in the lab and we're taking measurements and we're grinding through calculations, hopefully they become a little bit more meaningful. All right, sorry this video ran a little bit on the long side today, chemists. Thank you for tuning in, and I hope you found this helpful.